Inference on a population proportion. This part is again very important. Why? Because why do we look for a proportion in the population? Because there will be some defective items during the process and during the production. We will have some items that are defective, and we would like to find the proportion of this from the sample, and we will estimate the population proportion also. So we can use the hypothesis testing. P represents the proportion of a population, and there will be normal approximation to binomial. Actually, we should be using binomial, but with some limits, with some criteria, we can pass on to using normal approximation. Again, we say the H0 is equal to P is equal to P0, P0, and H1, the alternative hypothesis, is equal to P is not equal to B0. And we will again use the normal table, normal probability table, and Z will be equal to, if X the number of defective items, we can say if X is less than n times P0, then we use this formula. If X is greater than n times P0, then we use this formula. Let's look at the example 4.5. Here it is said that P is equal to 0.1 and the number of samples taken are 250. Out of this 250, it is found that 41 of them were defective. Alpha is again 0.05, so we will form the hypothesis testing. H0 is equal to P is equal to 0.51 and H1 P is not equal to 0.1. Let's look at the NP. Are we going to use this formula or this formula? N times P is equal to 25, so 25 is less than 41, so it is this part of the equation. We will use this equation. So x minus 0.5 minus n times p all over square root of n times p times 1 minus p. So 41 minus 0.5 minus 250 times 0.1, which is 25, and all over 250 times 0.1 times 0.9, and we'll take the square root of this value. So we have found that Z0 is equal to 3.27. So we had alpha 0.05. Is it two-sided or one-sided? Because it is said P is not equal to, it is two-sided, and when it's two-sided we have to divide alpha by 2. So we look at the Z table to 0.025, and that's 1.96. Since 1.96, well, this value 1.96 is closer to target value, or the calculated Z value is so far away from 3.27 and it is in the rejecting region, so H0 is rejected. P is not equal to 0.1. We reject the null hypothesis saying that P is equal to 0.1. Let's try to find the confidence interval of the population proportion. So we will determine an alpha value, subtract from 1, and it will give most probably 95% confidence interval on a population proportion P. P, what is P? Frequently corresponds to the to a lot or process fraction non-conforming. So we wouldn't like to produce those kind of products. If a random sample of n observations from the population has been taken and x non-conforming observations have been found in this sample, the unbiased point estimate of p is equals to x over n. If n is large and p is greater than or equal to 0.1, let's say, then the normal approximation to the binomial can be used. So in place of binomial, we use normal approximation in these circumstances when n is large and when p is greater than 0.1. So the confidence interval formula will be p hat minus z alpha over 2 square root of p hat times 1 minus p hat all over n. This is the lower bound, and the upper bound, you see that only this plus and minus signs change. Let's look at an example. In this example, we use the confidence interval and both-sided. So here n is equal to 80 in example 4.6, x is equal to 15. Let's look at the p-value. P-value is x over n. 15 over 80 is equal to 0.1875. A 95% confidence interval is asked, so alpha value is 0.05 because of 95, and z, because it is both-sided, confidence interval, it says alpha over 2 is 1.96. So when we put the values in places, like this was the p-value that is calculated from the sample, that's its proportion. We write this proportion, then we write 1.96, that's the z value, alpha over 2. That's again the p-value minus p all over n. So this is the positive part, that's the negative part, lower and upper bounds, and this is the result of example 4.6. We will be solving these kind of problems in the lesson.